Okay, so welcome everybody to our seminar. So for those who are here for the first time, I think there are a few, this seminar is organized by our network. It's a Latin American network on electromagnetic effects in strongly interacting matter. If you want to know more about this, just send me a message after the talk. Or if you just want to follow our seminar, also please send me a message. I will subscribe your email. So today, I'm glad to have with us Daniel Brandenburg. He will talk to us about latest results on mapping the ultra strong electromagnetic fields that is produced in heavy ion collisions. And let me briefly present our speaker. So Daniel got his bachelor from University of Florida. He got his PhD from Rice University. And from 2018 to 2020, he got a postdoc position at Brookhaven National Laboratory. And from 2020, he got a Goldhaber Distinguished Fellowship, also working at BNL. So Daniel was the first to direct measure this linear Breit-Wheeler process, which he will talk to us about today. And together with this, he and his group discovered the vacuum beam refringence. So for this work, he was awarded Best Talk at Quark Matter in 2019, winning the Elsevier Nuclear Physics Young Scientist Award. So he got other awards along his career, also for this work and for others. And since 2018, has been a software coordinator at Star Forward Upgrade. So I think most of us have been waiting several years for concrete measurement of this electromagnetic field. So it's a pleasure to have here the person who was responsible for this. And thank you very much again, Daniel, and the microphone is yours, please.
Well, thank you, Anna, for the introduction. Very nice introduction, and for the invitation. So it's an honor to speak with all of you, and I hope that on behalf of experimentalists, I can do a good job of interfacing with you, and hopefully we will have some interesting ideas that we can discuss. So what I want to do in this talk is really to try to focus on some of these experimental catalysts, as I call them, that have come out in the last few years, both from myself, from STAR, and from other experiments in high energy nuclear physics, and to really look at how those lead to open questions and how we can continue to pursue understanding these very strong fields. So with that in mind, I'm going to start, with a very quick introduction, and then I'll try to go through these measurements, which I call catalysts. And then I want to try to spend most of the talk on these open questions. And the format, I suppose, is up to you guys. If you would like to interrupt me with questions as we go, I leave that up to you all. So let's go ahead and get started. I think many of you know much better than I why this is an interesting topic. But I just tried to list, even for my own education, what are some of the reasons why we're so interested in not only the inner dynamics of QCD, but specifically the overlap of QCD, simultaneous with these very strong electromagnetic fields. So of course, there's potential effects on the transitions that took place in the early universe. I'm a fan of astronomy, and so I'm always interested in the connections that our fields can have with astrophysics. And one of the cases where we have this coexistence of QCD type matter with very strong fields is in some types of neutron stars. So over here is kind of a depiction of a neutron star with these magnetic field lines. And this is a case where there's still a lot that's not fully understood about neutron stars and about the kind of phase that exists inside where it's quite dense. In our own field, there's been a huge amount of interest over the last couple of years, especially at the relativistic heavy ion collider, to try to find evidence for chiral anomalies that are driven by this coexistence of strong electromagnetic fields plus non-trivial topological structure of QGP. And I won't talk a whole lot about this, but I think this is a huge push in our field, and it's while there have been some developments, I think there's still a lot of open questions. So I'll mention a little bit more about that on the next slide. And then this is related to the first bullet, but of course, I know some of the papers from Anna and others in this group have looked at how the phase transition boundaries, for instance, may split between the chiral transition and the deconfinement transition in the presence of magnetic fields. So there's just really a lot of these questions that are related to QCD matter in general, and then even more so when you add these strong fields. And then the last two bullets, I think, are a little bit more like approaching QED for its own sake. So in high energy nuclear physics, even though our primary goals are nuclear physics or to understand QCD, it turns out that because of these types of interactions, we actually have a very unique laboratory for studying QED in its own right. And those really strong fields and those unique QED processes in turn give us a unique way of probing QGP properties. So I think there's really, benefit from many different directions. I hope I can convince you of that in this talk. So as I mentioned, there's a huge push to try to observe this phenomena called the chiral magnetic effect. So very briefly, the idea here is that if you have a magnetic field which is produced simultaneously with a quark-gluon plasma that achieves chiral symmetry restoration, then you can produce an anomalous current in the direction of a magnetic field, and this will show up as a separation between particles of different charges with respect to a global event plane that's related to the impact parameter of the colliding nuclei. And as I mentioned, this was a huge effort that was put forth by our entire field, experimental and theoretical, but specifically the relativistic heavy ion collider ran an entire year of data collection using these isobaric nuclei, ruthenium and zirconium, with the idea of specifically isolating the difference from the electromagnetic fields, because these are isobars, so they have the same total mass but different protons. And the unfortunate result is that what this figure here illustrates is that the naive expectation was that a signal would show up as something above 1. And unfortunately, all of these analyses, which were carried out in extreme rigor via a blind analysis, actually ended up showing something smaller than 1, which really raised this question of how did this come about, and is there any evidence, therefore, for this chiral magnetic effect? And at the end of the day, one of the questions that started coming up was, well, how well do we really know the electromagnetic fields, even at the initial state? And so, for instance, you might think to yourself, well, it's QED, it's very simple, but there are some questions that you can ask. So, for instance, what is the low X behavior of these fields? What is the lifetime of the field? So is it just the vacuum lifetime due to the passing, or is the field trapped in some way? Are there observable effects due to event-by-event fluctuations of the subnucleon structure? And all of these things in principle could affect the observation of a chiral magnetic effect, as well as many other things that we search for in heavy ion collisions. So with that, like I said, just a very brief motivation. So now let's think about how these pairs are actually produced, because we're going to look at primarily lepton pairs that are produced from strong fields. So in the paradigm of QED, these types of interactions were already explored in the early 1930s, but as QED developed, it was really Julian Schwinger who developed the robust description of pair production in strong fields. And so Schwinger describes the breakdown of the vacuum above a critical field strength, which is related to the mass of the electron. And it gives you, a critical field strength in terms of electric fields, something on the order of 10 to the 16 volts per centimeter. So this is a really strong field. And there's been quite a bit of experimental interest in achieving a breakdown field like this. And actually, some of the early experiments in heavy ion physics were to try to get these highly charged nuclei close together so that you get a static Coulomb field large enough that the vacuum becomes unstable. As far as I know, there's been no definitive observation of that type of vacuum pair production. But in the heavy ion case, we do produce very strong fields. And if you just do kind of a back of the envelope calculation based on the charge and the velocity and the separation of two high energy heavy ion collisions, you get this, like I said, order of magnitude, which is really close to this critical field strength that Schwinger predicted. However, this effect is really only applicable for long-lived fields, or at least fields that are somewhat static with respect to the electron creation. And the issue in heavy ion collisions is that we're dealing with extremely short lifetimes of the field. So if you think about the passing time as these ultra-relativistic nuclei pass one another, it's a very short overlap time. So instead of dealing with these in terms of static or quasi-static fields, we really need to think of them in terms of quanta, so the equivalent photons that are manifest from these fields. So the idea here, or the paradigm here, comes from the fact that as you have these ultra-Lorentz contracted electromagnetic fields from these very fast-moving nuclei, what you end up with are these very pancaked electromagnetic fields that are, to a very good approximation, traveling like linearly polarized electromagnetic waves. And what we can do then is we can apply the Weizsäcker-Williams equivalent photon approximation. And by doing that, we can really come up with a robust description of a few different photon-mediated processes. So throughout the talk, I'm going to talk mostly about the two-photon interaction. In the case of real photons, this is the Breit-Wheeler process. And the idea here is that you can have a photon manifest from the field of each of the two nuclei, and they can interact through a lepton anti-lepton pair. So this is a second order in alpha, and you can produce this pair essentially because we have both high energy due to these ultra-relativistic nuclei, but also because we have high charge. Z alpha is close enough to 1 that we have a sufficient photon density to actually achieve these higher order processes. And then we can actually do a similar process, or achieve a similar process, where instead of having two photons meet and collide, we can have a photon from one field of the passing nuclei fluctuate into a quark-any-quark pair, which interacts via a pomeron or a region with the other nucleus. So the idea here is that, like I said, the photon, which has the same quantum numbers as a vector meson, can essentially fluctuate into a heady state, and then the pomeron gives it enough energy to become long-lived, and out emerges a real vector meson, like a rho 0 or a J psi, and then those can decay, giving us information in principle about the electromagnetic field through the photon, and about the gluon field through the pomeron. In this talk, I'm going to focus on what it tells us about the electromagnetic field. But okay, these two processes are what we're going to talk mostly about. And so with that, I want to talk about, okay, how can we actually use experimental measurements from these two processes to learn something at least about the initial EM fields. And so in this talk, I'll kind of make this distinction between the initial EM fields, which are really, the fields in the absence of any special medium that's produced. So especially if you go back to this case, in what's called an ultra-peripheral collision, the nuclei pass each other far enough apart that you don't have any hadronic overlap. So you only have electromagnetic interaction. And this is what I mean by just looking at the initial fields. Later in the talk, we'll look at what happens when you actually produce a medium, which may modify the fields in some way. So before I dive into the measurements, I want to just give a quick introduction to the phenomenology here for the two-photon process, so that there's at least some familiarity with the kind of assumptions that are made and the kind of things that we should be sensitive to from an experimental standpoint. So the main idea when phenomenologically modeling this two-photon process is that we start with what's called the external field approximation. So what this means is that the heavy nuclei, as they pass one another, are undeflected, so they maintain a straight line velocity. And the assumption is that the photons are emitted by the coherent field of the entire nucleus, or at least the entire charge distribution of the nucleus. Now, based on this idea, you can start from the electromagnetic 4 potential, and there's really only a few uncertainties in this description. So one of them I said is this assumption of the non-deflection. The other one is the form factors, which you see here in F. So that's like the nuclear charge distribution. And then there's the photon momenta. So I mentioned earlier, one of the goals that we have is to really try to understand how the field manifests itself across all different momentum spectrum or momentum ranges. So these different assumptions are built into these electromagnetic 4 potentials from which the rest of the calculations take place. And one of the things that I want to point out here is that when you apply this via the equivalent photon approximation, it gives you a pretty intuitive and straightforward way to think about these processes. And the idea here is that the photon density is proportional to the time averaged energy flux, which is what you see here. And so this kind of gives you some inherent connection to the field. Oh, I see a hand from Alejandro. Please go ahead.
Oh, yes, thank you. If you can go back to your previous slide, I saw that there is like a relative phase between one and the other fields. Can you comment on that?
Right. So this takes into account the fact that they are coming from. So basically, you have two sources, and you can do some dimensional reduction so that instead of thinking of two impact parameters, you can actually just express it in terms of just the impact parameter between the two nuclei. But then you need this additional phase.
Right. So see this. You're saying that this tau index here in K1 is what, the transverse direction? It is the transverse direction. Right?
Yes, this is only in the transverse direction. Right. Because in this, in this approximation, you basically don't even worry about the tiny contribution in the longitudinal direction.
Right. Thank you.
Yep. Yeah, good question. So like I said, we'll talk more about the long-lived effects. But the other thing that I pointed out, which again is probably obvious to many of you, is that just from the cross-section alone, so just from the rate of the production, we can learn something about the electric field. But at least in principle, a magnetic field can't separate a pair from vacuum. And so if we want to connect this to these measurements from the electric field to the magnetic field, we need some additional information. And I'll talk about what that additional information is as we go forward. So the idea here is that this basic phenomenology has been available for about 20 years. So a lot of times the obvious question then is, well, what's new and why are we pursuing this, as active research? And that's where, like I said, I really I tend to think about this in terms of the experimental catalysts that have challenged our understanding, at least challenged my understanding of this process. And one of those that came out over the last few years, I show an example for both of these photo processes, is that for a long time it was thought that you can only have these photon-mediated processes in these ultra-peripheral collisions where there's no hadronic overlap. And as I pointed out to you, the assumptions of no deflection, so straight line motion, and coherent emission from the entire charge distribution, they really are pretty fundamental to this assumption that you don't have hadronic overlap. However, over the last several years, in STAR, we discovered that you can have the photon-photon process even in 60 to 80% central events. So those are kind of, they're not head-on, but they're kind of glancing collisions. And what's shown here is that you have this real obvious excess of electron-positron pair momentum at this relatively small value, which is consistent with this photon-photon process. And if you take into account all of the other production of dilepton pairs from a quark-gluon plasma or hadronic interactions, you get this smooth curve, which really does not explain this excess at low PT. And a very similar thing is found in photonuclear events. So Elise looked at J-psi production, again in these glancing collisions. And what they found is that, again, you have this really large excess at very small transverse momentum. And if you compare that to the expectation for coherent photoproduction of these vector mesons, you see that it agrees very well with the measurements. So fast forward a couple of years now, I would say no one doubts this effect. There's significant excess yield at these very low transverse momenta. The reason it's concentrated at low transverse momenta is because the photon PT or KT in this process is always very small. And again, that comes from the fact that the fields are extremely Lorentz contracted and are almost parallel to the beam direction. So these are clear signature of photon-mediated processes, even when you have this hadronic overlap. So this is interesting because it gives us a QED probe in situ with, potentially a quark-gluon plasma or a system that could produce a quark-gluon plasma. Now, you can actually take this even farther and go all the way to head-on central events. So over here, this is a measurement of dilepton acoplanarity, which is just a measurement of how close to back the pair is. So this measurement is from Atlas in muon production, and they go all the way to the 0 to 5% central centrality band. So we're really looking at head-on collisions in principle with B equals 0. The entire nuclei is colliding. And what they find is this very significant broadening. And at first there was some confusion as to whether or not this was from this photon-photon process, but it's now been shown conclusively that it is. And in order to understand this broadening effect, people have come up with very creative ways to test the impact parameter dependence of these processes. Now, the reason the impact parameter dependence is interesting is because I think we're all familiar with the uncertainty principle that tells us in quantum mechanics that if we localize in position, or another way of saying that is fixing the impact parameter, that should lead to some uncertainty on the transverse momentum of the observed process. Now, it turns out that that's a little bit of an overly naive look at this process. And so what we've discovered through these creative attempts is that you can, in fact, find ways to fix the impact parameter and observe this process to see what the relationship is between impact parameter and the transverse momentum of these processes. So CMS has pioneered some of this, in which they look at the 0-degree calorimeters that see the neutrons that are emitted from these events that have very close passing but no hadronic overlap. And what they can do is, based on the number of neutrons that they see they can, at least on average, select these ultra-peripheral events that have a relatively large impact parameter or a relatively small impact parameter. So for those of you who are familiar with the Glauber approach in experiment, it's kind of like a parallel to this, but in ultra-peripheral collisions, where you really don't have any event activity that you can use to correlate with the impact parameter. So CMS published this in Physical Review Letters last year, where they look at this back-to-backness or this acoplanarity, and they see a very strong effect with respect to this number of neutrons, which again is related to large impact parameters versus small impact parameters. And what they showed was that these traditional calculations that have been done over the course of many decades, which ignore this effect, really cannot explain this data. And in fact, if you take this account into effect, you can see that this trend is well reproduced, even if the absolute scale is a little bit off. So the question here is, what do we actually learn from this? And I think we can learn from each other. And STAR has actually continued to explore this effect. And instead of looking at the acoplanarity, we can actually look directly at the momentum of the pair that's produced. And we see this effect very clearly, not only in dielectron production, but also in dimuon production, where the traditional EPA calculations, given, for instance, by Starlight, really predict this much narrower PT distribution. But if you take this impact parameter dependence into account, what you end up getting is this broader distribution. And that actually shows us that we have this sensitivity. And the reason that we have this sensitivity is because if we look here on slide 21 on the left, we have the fields that are overlapping. And depending on which impact parameter we're at, we're looking at different energy photons and also different geometry of how they collide. So the really interesting thing here is that when we look in this transverse plane, where the nuclei are passing, one's going into the screen and one's coming out of the screen, we can think about this in terms of the semi-classical electric and magnetic field lines. Now, because these are ultra-Lorentz contracted, if you look at any small point in space, you have a case where the electric and magnetic field lines are perpendicular, and they're also perpendicular to the direction of travel. And like I said earlier, this is characteristic of a linearly polarized electromagnetic wave. And so what this means is that when you have a photon which is locally manifest from these fields, let's say you have two photons which are manifest at this point, somewhat equidistant between the two nuclei. Those photons essentially have polarization vectors, which are defined by the semi-classical electromagnetic fields. And therefore, you can actually define the angle between their polarizations. So if the photons collide kind of equidistant between the two nuclei, you expect somewhat of an anti-parallel polarization. If they collide kind of off to one side, you're much more likely to have something closer to a perpendicular angle between their polarizations. Now, the reason that this is interesting is because it gives us something like a two-dimensional view of these photon-photon interactions. And I'll show you in more detail as we go along. But the interesting thing here is that we now have, kind of two pieces of information to look in two dimensions. So what I'll show to you is that the pair transverse momentum, so the transverse momentum of the electron-positron pair, is related to the location in space that the two photons collide. And then on top of that, you have this polarization effect, which is related to the location in space where the two photons collide. Now, the reason that some of these features, I think, were not pursued in greater detail for many years is because when we have these heavy ion collisions, the impact parameter is random from one event to the next. You don't know which way it's aligned. You don't know, how large the impact parameter is. And so experimentally, it's extremely challenging And in fact, if you have no way of aligning these impact parameters, then any effect due to this, kind of two-dimensional view of the nuclei will wash out over many events. And so the real breakthrough came from some theory friends that realized that you could actually find a way to orient the events from one event to the next so that these types of events don't actually wash out. And in the end, it ends up being a very simple experimental observable, which is that if you have this electron-positron pair or muon pair, you can define the pair transverse momenta, which is just the sum of the daughter 4 vectors, and the difference between those daughters. The angle between those two turns out that it's related to the polarization basis of these interacting photons. So what I mean by that is it's essentially a proxy for the angle between the two photons' polarization. It's not exact because you have some resolution effects from the decay, but it's a good proxy. And the prediction here is that if you can observe the photon's linear polarization, because of the fact that these photons interact at all different locations in space, you end up with kind of a competing effect where when the photons collide with anti-parallel polarizations, you get a negative anisotropic modulation. And when they collide with almost perpendicular, you get the same modulation, but with an opposite sign. So when you put all this together, you end up with some weighted average of this positive and negative effect. And that's exactly what we measured in STAR, both in ultra-peripheral collisions, so these large impact parameters, and in the black, it's the glancing collisions, where you just barely overlap. And what you can see here is a very clear, very strong cosine 4 delta phi modulation, which is exactly the prediction for linearly polarized photons. And we see it in ultra-peripheral collisions. It's extremely consistent with QED predictions. So the red is the fit to the data, and the blue dashed line is the QED prediction. And as you can see, they're almost on top of each other. Now, as you go to these glancing collisions, there's quite a few things that might change the picture. There's the impact parameter dependence of the QED process itself, but then there's different ways in which the produced medium could actually interfere with or even maybe enhance the fields that you see. So the idea here is that we've observed a couple of different interesting experimental observables. And over the last couple of years, I would say there's been a lot of theoretical description or a lot of theoretical progress that's led to a very rigorous description of this two-photon process. So for instance, there's been approaches based on Feynman diagrams for the QED calculations. There's a couple of groups that have looked at describing this in terms of the photon-Wigner functions. And I think this is a quite interesting approach because it gives you an idea of the spatial and momentum dependence of the process. It's been looked at in terms of classical field approximation and exact results from this group of strong field QED theorists looking at stochastic plane waves. So really a lot of people have thought about this process, and the key characteristics that we observed experimentally and we now have theoretical description for is that the coherent photoproduction processes are possible even in these events with hadronic overlap. The photon momentum is determined by the electromagnetic field distribution. So what I'll talk about next is that we can actually use that to map the spatial extent of the fields. And as I just showed you, we have experimental proof that these photons are linearly polarized and are therefore sensitive to kind of the two-dimensional distribution of the electromagnetic fields. Alejandro?
Yes, sorry for interrupting again, but can you go back one slide?
Mm-hmm.
I see that the 60 to 80% distribution is multiplied by 0.5. So I'm just curious, the strength of the signal is as large as for the ultra-peripheral, right?
Yeah, so the strength of the signal is actually larger. It's just multiplied by 0.5 to scale so that you can put them on this same axis and see them simultaneously. I didn't include the table here, but we observe in UPC, we observe the effect. So the strength of this modulation is about 17%. In the QED case, it's about 30%. So it is stronger in the 60 to 80, but it's scaled down just for visual purposes.
Mm-hmm. Okay, that was just an observation. Thank you. This is a good piece of information. Thank you.
Yeah, thank you. And so just to give you another kind of visual of this, the idea here is that depending on where these photons interact, you are sensitive through the transverse momentum of the photons and also this polarization angle. So at very large impact parameters, this heat map tells you the photon-photon overlap probability. So at very large impact parameters, you have the weak part of one field overlapping with the strong part of the field from the close nuclei, and then vice versa. So when you put that together, what you end up with are almost all interactions happen in like a circle near the two different nuclei. Because the electromagnetic force is long range, there's no problem here. But what this does is that it means that you, at very large impact parameters, you almost average over all the angles, and you get a transverse momenta, which is kind of fixed to this region where you have the strongest part of the field. But you can imagine that as you move this to smaller impact parameters, you start to be more sensitive to the two-dimensional aspect of the electromagnetic fields, and you start to become more sensitive to overlap of the field, where it's, instead of just being confined to this one area that's the strongest part of the field. And I'll give more examples of that. So what I've tried to do again in this first part is to just look at the tools that we've developed over the past couple of years. And like I said, there's already been some theoretical progress. And so we have a lot of confidence in some of these aspects, but now this leads to many open questions that we'd like to understand more. So this is where I hope I found something in here that is interesting to you. So I went back through some workshops that we've done recently, and I looked at some of the open questions that people have brought up with respect to these topics. So I'm going to try to cover several of these. Instead of going in real in-depth detail, I wanted to kind of go through this laundry list with the hopes that I would pique your interest on at least one of these topics. So one of the things that we can do, which I tried to show you over these last few slides, is that by using these processes that really give us sensitivity to the spatial distribution of the fields, we can actually constrain the charge distribution and therefore the initial electromagnetic fields that occur in these heavy ion collisions. We can really ask the question, what is the origin of this coherent emitter of the photon? And so that's related to charge stopping. We can also then ask ourselves, is there any way that we can understand better the effects or the signatures of long-lived electromagnetic fields? And again, the idea there is that if you have a collision which produces a quark-gluon plasma, is there any signature of a field being trapped in this quark-gluon plasma due to some conductivity? You can ask about the energy dependence, and you can ask about the event-by-event fluctuations of the protons within the nucleus and how that might affect the fields that you observe. And then finally, if I have time left, I'll just mention a few applications for beyond the standard model physics as well. Okay, so to start with, in our field, in high energy nuclear physics, we have historically always just taken low energy electron scattering data about the heavy nuclei, and we use that, we extrapolate that to high energy, and we use that for our Glauber calculations, for our cross sections, for everything. And one of the ideas that I had for this for this measurement was, can we actually use this to constrain the electromagnetic fields that we see at high energy without necessarily having to rely on the low energy scattering data. And what I showed you a few slides back is that the calculation that goes into these processes really starts with this electromagnetic four potential. So from that, you really have a handle on the field, the electric and magnetic field that are going in. And without going into too much detail, what you can do is you can just run that calculation with arbitrary four potential input and minimize against the experimental data and ask the question, what four potential is allowed based on the measured photon-photon to dilepton production. So by doing this, we can actually carve out a confidence band for what the charge distribution of the nucleus looks like at high energy. And so what you see over here is actually being shown for the first time at Quark Matter tomorrow. And it's a combination of the published results from the paper where we first pioneered this. And then we've combined the ultra-peripheral collisions with the hadronic overlap collisions. And then a student that's working with me has also added the same analysis at lower collision energy. So at 54 GeV instead of 200 GeV. And I want to point out just a few, I think, interesting impacts of this. One, we seem to see a little bit of tension or difference in the observed charge distribution as a function of energy. So specifically what we see is that as you go to higher energies, it's almost like the charge distribution is swelling a little bit. Now the overlap here where you can see this darker overlap, that's the 3 sigma kind of edge. So there's not, terrible tension, but there is certainly some hint here that the charge distribution that you see may be effectively different as you go to these higher energies. And actually, this is where my hope is that the LHC experiments will continue this analysis, and that way we may continue to have even more data points. Maybe LHC will be up here and could possibly really show us more of a trend with respect to this energy dependence. The other thing that we can do, which is really related to the question I brought up at the beginning of the talk. So I mentioned to you this search for the chiral magnetic effect, and that when the results came out, people were somewhat confused. And one of the questions that came out was, well, how well do we really know the initial magnetic field of these two isobars? And are we really sure that they're different by the amount that we expect? Otherwise, your whole argument for observing this chiral magnetic effect really evaporates. And so my group wanted to try to, really provide some experimental input on this. And so what we did is we measured this photon-photon fusion process in ruthenium, and in zirconium. And what we can do is we can look at this as a function of the momentum. As I showed you several slides back, at very low momentum, the production should be dominated by these electromagnetic phenomena. Whereas as you go to higher momentum, it really should be dominated by hadronic processes. So what that means is, at very low momentum, it should scale with the strength of the electromagnetic fields, which is in fact what we see, though the error bars are still somewhat sizable. And then as you go to higher pair PT, you really get what you expect, which is that the hadronic production from these two isobar are very similar, and therefore the dilepton production from hadronic sources is consistent with one. So again, this is evidence that the electromagnetic fields really are different by the amount you expect, and the nuclei, the actual mass of the nuclei are similar the way you expect based on them being isobars. Now we can look at this again with the photonuclear process. So again, we can do this for ruthenium or zirconium, and produce a J psi, which we measure through E plus E minus. And the idea, again, is basically the same, which is that at low pair transverse momentum, it should be dominated by this photonuclear process. Whereas as you go to higher transverse momentum, you just have hadronic production of J psi, which should not scale with the electromagnetic fields. So due to the error bars, this is a little bit weaker. But if you put these two measurements together, what we find is at 3.5 sigma significance, we find that the isobaric electromagnetic fields really are different in the ways that we expect. So it's at least evidence that there's no, washing out of the electromagnetic fields, which might be responsible for the lack of observation of the chiromagnetic effect. With that, I want to move on to another open question, which is that you can ask yourself, when you actually have these hadronic interactions, what is actually coherently emitting the photon? Because as you can see over here on the right-hand side, it's pretty obvious when you have these ultra-peripheral collisions that you can have a coherent field produced by the entire nucleus. But when you start to have a glancing collision, it's a little bit less obvious. Maybe your coherent emitter is only the part which is not stopped and continues on, meaning the spectator. But then you can actually make even more combinations like this, especially when you're thinking about, in the photonuclear process, what emits the photon and what emits the gluons. And so STAR has measured, again, it's this J psi measurement. And over here on the left, what you can see is you can look at the production rate for all of these different hypotheses. So the hypothesis where the coherent emitter is the entire nucleus versus only the part which is not stopped and carries on, or the spectators. The uncertainties are still large, but there's a hint that maybe it is this spectator-spectator case, which again makes sense based on this assumption that the nuclei that emit the field are not deflected, and that it's a coherent emission. And if you have a breakup due to collision, it's a little bit hard to imagine that you keep the coherence of the nucleus. Again, though, the uncertainties are still kind of large, so that's still going through active investigation. And we actually just added here the same analysis for ruthenium and zirconium. And as you can see, this process really scales with Z squared. And on this plot, you can kind of get an understanding of how large our experimental uncertainties are here and why it's hard to make a strong statement about what's the emitter in these different scenarios. So let me go ahead and move on to the next topics. But again, I think this is really interesting because it's really testing on these assumptions. Oh, I do have this one new measurement from ATLAS that I wanted to include. So as I pointed out earlier, ATLAS is able to measure this photon-photon fusion process to dimuons in these head-on central collisions. So again, this is really where you have an impact parameter close to 0. And what I show you here is the theoretical prediction for the Photon-Wigner calculation. And this is assuming all of the same assumptions I showed earlier, which is that the entire nucleus emits the photon with no stopping. And it's actually striking how well this prediction describes the data. There may be a little tension. The data may be a little bit broader than the theoretical curve, but the overall cross-section and the overall shape of the data are fairly well described by this calculation. And again, this is without any stopping or deflection. So I think this just really opens up some questions of how this could be the case. So I'll leave that topic for now and move on to some ideas for how to search for medium effects. So as I mentioned earlier, when you have these fields cross in vacuum, so that's what this dashed line represents, you have an electromagnetic field which is very strong for a very short period of time, just as the nuclei pass one another. But there's been quite a lot of work over the last few decades to think about what would happen if the produced quark-gluon plasma has some effective conductivity that's able to really trap the electromagnetic field and potentially cause it to be longer lived. So, for instance, here are different values of this sigma LQCD. If the field is trapped, really close to its strongest point, you get something like the blue dashed line. And then if it's trapped at a later time, you get something like the black line. But either way, the idea is that if you trap the field for these longer lifetimes, you now have a very strong electromagnetic field that may interact with the produced electron-positron pair or the produced other object, whether it's a vector meson or something else. So in 2018, Starr thought about this concept, and from a fairly naive approach, just asked the question, what would happen if you have this long-lived field which causes Lorentz force bending of a pair that's produced by this photo process? So the idea here is that if you have an interaction which produces a quark-gluon plasma and traps the field, and you also have a dilepton pair produced, could you have Lorentz force bending which modifies the kinematics of that pair? At the time, we didn't fully understand all of this impact parameter dependence, so we used what we now know is the wrong baseline for this calculation, and so the value of B that we extracted was clearly too large based on what we know now. But the procedure itself, I think, is still somewhat applicable, which is to allow these E plus E minus to experience a field and see what happens to the kinematics of this process. I just want to point out that that's one of the advantages of these processes, is that because you're dealing with a pair that's produced at such low transverse momenta, even small effects could have observable impacts to the final distribution. So since then, there's been a little bit of work done that shows that there should be a strong rapidity dependence to this Lorentz force bending, and that it should saturate once you get to more than 3 units of rapidity. So for those of you who aren't familiar with the Starr detector, we only cover plus minus 1 unit of rapidity. So this is one of the main experimental challenges, but it's something that the LHC experiments cover a much broader range and may be able to really test this, this hypothesis. Even with that limitation in Starr, we have already been approved for running through 2025. And what I show you here is what we call the mean PTE, which is basically, it's just a way for us to measure how much impact parameter dependence or how much broadening you get to the dilepton spectrum. And we now know with this very high precision QED calculation that we do expect some change due to the impact parameter dependence and the invariant mass of the produced pair. In the black, we show our existing measurements, which you can see are still systematically above this line. And in red, here are the predictions for what we will be able to achieve over the next 3 years. So the idea here is that if there are medium interactions, we should be sensitive to this by virtue of a disagreement with the QED baseline. Again, because the QED baseline is really just the vacuum effect. Now, we actually went back and reanalyzed our old data with this new and improved QED calculation. And if you look here on the bottom figure, this is the measurement in 60 to 80% collisions of the electron-positron momentum. And then this dashed line is the QED prediction. So as you can see, it does a pretty good job of describing the data. However, what we find is that the absolute best fit to the data, albeit with large uncertainties, is an additional broadening of about 14 MeV. Now, this is really interesting because if you look at an array of other measurements that have been done that are not yet sensitive to electromagnetic lifetime effects, but are nevertheless beginning to put a constraint on how large those could be, this number on the order of 10 MeV is from my understanding, about what we expect for a final state electromagnetic field effect. Now, I think I'm running out of time, so I'll go a little faster, but we can actually look at this also by looking at the energy dependence of this process. So as I mentioned earlier, STAR has now measured at top energy of 200 GeV, and then also at 54 GeV. And we hope to add even more measurements at lower energies. The hard part is that the cross-section really falls pretty quickly as you go to lower center of mass energies. But for now, we have these two different measurements at these two different energies. And what we can do is we can compare these to the corresponding QED calculation for each case. So for instance, in the magenta, we have ultra-peripheral collisions at 200 GeV. And then as you go up, we have the QED prediction for the different centralities as a function of the center of mass energy. So as you can see, the QED calculations predict some energy dependence in this observable. But what we observe, again, with somewhat large uncertainties, is that we're systematically above the QED prediction. So if you just focus on the 200 GeV points, we're systematically above the QED prediction, even taking into account all these additional effects that I've discussed throughout the talk. So what we can say then is, by looking at all these data points, we can test two different hypotheses. We can test the QED prediction of energy dependence by comparing 54 to 200. And we see that pretty obviously, even with these large uncertainties. And then what we can do is we can compare the QED calculation at a given energy to the measurement and ask how much of an excess or how much of an additional effect do we see. And again, we do have a systematic effect, but it's only at about the 2 sigma level right now. So what we want to do is we actually want to try to understand this more fully. And one of the competing effects that might modify these distributions without necessarily having a final state, long-lived electromagnetic field present are fluctuations of the nucleus that could modify the event-by-event electromagnetic field. So the idea here from this paper by Skokov is that if you have these proton locations which are fluctuating from one event to the next, on average, you might have a very smooth field distribution, but you could have some events that are much stronger at small distances, or even weaker at certain distances, just due to how the protons are distributed in space. And the other point that this lower plot shows is that this can also affect the direction or the alignment of the magnetic field. And as I pointed out earlier, we're sensitive to the polarization of the field, which should be modified if you're fluctuating the field in such a way that the geometry is really changing. So the idea here is that we can look, I'll skip this one, that we can look for the evidence of these event-by-event fluctuations. So what I'm showing you here is, again, new measurements that are going to be shown tomorrow at Quark Matter, where we have really detailed measurements of dilepton production at 54 GeV. And at very low transverse momenta, it's well described by this coherent QED interaction. At higher transverse momenta, it's really well described by just purely hadronic sources. However, we have this region in between where there's a bit of tension. We clearly are not describing the production with either of these two sources. And it really seems to persist across collision energies and also across centralities. I just showed you these two as an example. Now, ATLAS has measured the acoplanarity, as I showed you earlier. And what they've done is they've actually considered what we've started calling the semi-coherent process. So the idea is that you have an electromagnetic field from an individual proton, which can interact with the coherent field of the other nucleus. Now, this process is going to be suppressed because of the fact that that field from just one proton is so much weaker. But because you have so many protons in one nucleus, you actually end up making that suppression back up to some degree. So there's the idea that maybe you can actually observe this effect. And if you really are sensitive to the field of these individual nucleons, there's been some discussion that maybe we can actually observe the impact of event-by-event fluctuation of the proton distribution. And part of the idea there is that this bump is right around 200 MeV. And if you just take one Fermi and you convert it to the energy scale, you're looking at something that's about at the right place to be related to the field of the proton. So I would say I just wanted to propose this as an interesting idea. We definitely don't know what's happening here yet. And then I think I'll just end with this final look, which is that, as I mentioned earlier, as you go to these smaller impact parameters, you really are probing a different geometry of the overlapping fields. So the idea again here is that the color map tells you the photon-photon overlap probability. So as you come to these smaller impact parameters, you become much more localized. Your production is much more likely in a small region of coordinate space. And that translates to a much a range of photon-photon polarization angles that's much more constrained. And so we expect this modulation to get stronger as we go to smaller impact parameters. But if you have any kind of bending or final state interactions that could randomize the direction of the particles that you measure, then that'll reduce the strength of this modulation that we observe. So this gives us another handle on how to potentially observe final state interactions, whether those are from long-lived effects or something else. And just again, to give you a prediction, we've looked at what we'll be able to do over the next 3 years. This is very similar to the plot I showed you a few slides back, but this time for this modulation strength, in UPC, we're already quite precise, so we're not going to gain too much. But as we go to the more central collisions, we'll be able to have the precision we need to potentially observe modifications from the QED prediction. Again, this is the predicted uncertainty if we just keep the central value at our current measurement. So this is interesting because either way, if it gets stronger, we'll have the first experimental evidence of this impact parameter geometric effect from the magnetic field. If it gets weaker, it's evidence of something else happening. So I think either way, this will be an interesting result as we get more data to make a strong statement. Let me just end with one look at beyond the standard model. So light-by-light scattering has become a really interesting topic, especially at LHC, where they have the energy to achieve this alpha to the 4th power process. And one of the things that ATLAS and CMS have started looking at is the potential for observation of axion-like particles through light-by-light scattering. The idea here is that you can have the photon-photon couple through an axion instead of a QED loop. And in that case, the interaction is governed by this Lagrangian. And what I want to point out is that if you decompose it, you get this piece which is proportional to E dot B, which if we go back to these diagrams, what you begin to realize is that the E dot B is actually a subsection of the total cross-section. It corresponds to only a certain set of production locations in coordinate space. And so one of the things that my co-authors and I worked on was actually investigating if you could do these angular measurements like what we've done at STAR, if you could do these at the LHC, could you become more sensitive to this axion-like particle production? And the answer that we came up with is yes, you can become, mostly because experimentally, the cross-section, the absolute cross-section, is one of our biggest uncertainties. And the advantage to looking at these angular distributions is that they are unaffected by your overall cross-section normalization. So it gives you an independent handle, but also a more sensitive handle on what's going on in the interaction, whether it's a standard model interaction, or in this case, something new, which has a different structure, a different spin structure. So with that, I'll go ahead and end. I hope I found something that's interesting to all of you. The real thing that I want to emphasize is that we're just now getting to a place where we can experimentally constrain the fields that are produced in heavy ion collisions. There's quite a few other techniques from very diverse set of experimental measurements, which I think will soon be able to contribute as well, from flow measurements to many other things. But if we just think about what we talked about today, there's quite a few open questions as to what or how these fields are really behaving as you look in more and more detail. So I think there's quite a few exciting opportunities, and I hope I also convinced you that there's a lot of room for theoretical input so that we can guide each other as we have new experiments, and hopefully also theory input to understand those experiments. So with that, I'll end. Thank you again, and please let me know if there's questions.
Thank you, Daniel, for this very inspiring talk. So we now open for questions. Please, Lance.
Very nice talk. I'm glad to see a lot more rigor in the experimental analysis. I've just been around, seen a little bit this field from the outside as a strong field QED person by training. Can you go back to slide 31 or 32 or so? There was some discussion about spectator versus complete nuclei, the fields.
Did you want this one or maybe this one?
Maybe this one. Part of it, so the question was, and maybe this was just because it was an offhand remark by you, whether we could see some departure from coherence because of stopping and breakup, as a function of overlap between the nuclei.
Right.
We have to be. I think my thought on that is that we have to be a little careful there, right? Because coherence isn't something that has to do with, isn't a special state of two objects, right? It's just the fact that they happen to be in phase with each other.
Right.
So the low frequency electromagnetic fields, even if the protons are a little bit rearranged in the nuclei because two of them are stopped by overlapping with the other nucleus, the low frequency electromagnetic fields will still be largely the same, right? But then the decoherence will gradually appear in the higher frequency modes because of course those protons are now stopped, and that change in the charge distribution will propagate out at a time scale corresponding to their that stopping time.
Right.
On the other hand, that may be something that we can see, right? In a somewhat more advanced analysis, that momentum dependence may be the key difference in the coherence.
And I think, when you talk about the wavelength or the energy dependence there, one of the things we've thought about is if we could, as we gain more statistics, we can look at this as a function of the invariant mass of the dilepton pair, which we believe should be sensitive to this effect that you're talking about. Because I kind of presented it in a bit of a naive, because like you said, it's not a one-dimensional picture, right? But I think part of that is I'm not a theorist and I'm trying to present it maybe somewhat naively, but part of it is that this naive picture has worked so far. So it's very exciting to me that we're in a position where we can start to see things break down that really challenges, our naive pictures, at least us as experimentalists. So yeah, I
Right.
really I appreciate
Well, I
the comment.
mean, yeah, so, part of the reason those naive pictures is work, for me as a theorist, I think of those naive pictures working is that, our understanding of physics proceeds by having naive picture first and then refining that gradually, right? I mean, classic quantum mechanics is still classical dynamics, but now it's just your degrees of freedom are a little bit different. You have wave dynamics, and therefore you have interference, right? But ultimately, quantum field theory, the Lagrangian is the classical Lagrangian at leading order. So
yeah,
that's naivete is not a bad thing.
Mm-hmm. I guess the other thing I'll point out is that that's part of why. So, and if anybody wants to work on this, I'd be happy to work with them. I'm one of the co-authors on one of these QED calculations, and it's been on my to-do list for a long time to go back and try to analyze, do this exact same analysis that you see here for this photonuclear process for the collection of photon measurements from Rick and from LHC. And again, I think coming back to your comment, you should be sensitive to these differences also as a function of center of mass energy, because you're probing different photon energies. And so if you did kind of a global analysis of Atlas data and Elise data and data at Rick from Star and Phoenix, you may find something interesting where, again, if you look at kind of the size of the coherent emitter in some way, if you saw a trend that went with energy, I think it would be experimental evidence of what you're talking about, where it's not a one-dimensional picture, but it's the frequency of the photons or the energy of the photons that really relates to what's being stopped and how quickly. Is that from what I just said to you, does it sound at least like I'm understanding your point?
Yeah. I mean, the difficulty here was mentioned also in that a little bit studied by that Skokov work about the time dependence of the fields, right? Because it's right now, the experimental challenge, and this is where my biases in my background comes out. Is I just don't have nearly a handle on what sort of observables work for you.
Right. Yeah.
Because I think a little bit more in this frequency space, but that's not really something that you have very many ways to get an experimental handle on.
Right.
That is not obviously a challenge.
Right. I think, yeah. So I think my off the cuff response there is that we have invariant mass of the pair and we have the energy of the colliding system. Those are not direct, right? Those are not direct handles. They're just somewhat related. Yeah.
Okay, Malena.
Thank you.
Hi. Can you hear me? Thanks for a very nice talk. My question, I have a couple of questions, but at least one that strikes me is this very nice plot where you have the confidence level regions, where you have the skin depth and sort of like a prediction on, and this data point from low E scattering. My question is, in order to get to this point, you said broadly you ran a calculation using this kind of model that you explained at the beginning. And my question is, you mentioned that the way that you interpret this is that it's telling you that when you go to lower, or depends on how you see it, when you go to higher energy collisions, you have like a different perspective of like a swelling of the charge distribution. Did I get that correctly?
Yeah. So in order to make this plot a little simpler, we just drew the bands. But so what you can understand is if you just look at the blue, which is 54, the actual lowest chi-squared is somewhere kind of where the middle of my cursor is here. So it corresponds to, I think it's actually kind of here. So it corresponds to a radius which is about 6 Fermi and a skin depth or a surface thickness, of 0.5.
0.5.
And then if you look at the 200 GeV, both the ultra-peripheral and the hadronic events combined, your lowest chi-squared is something like here. So you're looking at something which is maybe just a tad larger in the, overall radius, but then prefers this kind of more spread out surface thickness. So either way, so actually one of the things that we're going to do to try to break, basically to make this more intelligible and kind of break this diagonal degeneracy here, is to just plot this as the versus the root mean square of the charge distribution. And we've already looked at this, but basically what it shows you is that if you take the radius and the skin depth, account together, they still overlap, but you favor something which is broader, a distribution which is somewhat broader at high energy and somewhat narrower at lower energy.
Yeah, I mean, my question then is, if you do this in the opposite direction, like from my perspective, where I take a simulation and I put these two ions to collide, and I use the skin depth and the charge radius as inputs of the Glauber, rather than in this exercise that you were showing, which is very interesting. So if I fix my skin depth and I have a radius for gold, and I have this kind of wiggle effect from the skin depth, then what I can play with is I can learn about the electromagnetic fields that are produced as in the initial conditions, and I can go to several centralities and see whether these electromagnetic fields are long-lived or short-lived. Especially if I go to really low collision energies, what we find is that they tend to be longer-lived. Instead of having like a fraction of a Fermi in the average life of these fields, you have like 5 Fermis or something. So the life of the magnetic fields are becoming comparable to the sort of scale of the radius of the ions that you're colliding in the simulation, right? From the simulation.
Right.
So now that you show this, and I guess this is you are making a mapping with some kind of a Glauber picture, right? In order to get this.
But this is a very simple, completely continuous static Wood-Saxon distribution.
Yes.
That's where I brought up. There's a lot of assumptions there, and a lot of things that are maybe not so realistic. It's just kind of a first, a very simple picture for how to interpret the data. But yeah, that's what we're doing here.
So in order to help in this discussion, would it help to have a study of dilepton production for low energy collisions, but with a scan in the geometric variables that we use in the Glauber, in order to sort of say something about this plot? What do you expect from?
Yeah. I mean, well, that's right. I think, we did this in an attempt to gain a bit more understanding or interpretation of our measurements. But like I said, we understand that there's some naive approaches here. So I think there's a couple things that I think would be interesting. One is to do exactly what you just said, do it more rigorously and kind of from, like you said, from the direction that makes more sense. The other thing is that we actually are about to come out with measurements of uranium. And this is interesting because uranium is not spherical, right? It's oblong, or however you want to say it. And this is an interesting case because it gives you maybe another handle on looking at some of these effects, and maybe not in that case specifically looking at the energy dependence, but seeing if we can, through these techniques, really observe this non-spherical geometry. So there's a lot of things that I think experimentally we're interested in. And then from a theory standpoint, the big things that stand out to me is what you just mentioned, and taking into account event by event fluctuations and, I guess, non-spherical geometries. What we've done is just really the simplest case, first look at this, I would say. So those are the things that kind of pop out to me.
Thank you. Yes.
Yeah, thank you.
Giorgio?
Hi. This is an experimental question and possibly a stupid one, but when you talked about the photon polarization, I mean, you kind of measure it indirectly by the angular modulation of the dileptons, right?
Yeah.
That's the. Is there any? I mean, in a slightly different context, I talked to an experimentalist in the past who said that in principle it's possible to use the detector as a sort of Stern-Gerlach apparatus to get a handle on the spin of the leptons. To get a handle on the spin of the leptons and sort of measure that directly.
Right.
And confirm that they're spin one, you know, that it's a
yeah,
spin one.
exactly. Oh, the pair is spin one, yeah.
Yeah, is that realistic in any way?
I'll tell you, it'd be very interesting. I don't know. I'd be curious who will mention this to you because I'd love to talk to them. There have been a lot of discussions that I've heard of, maybe not so much for this process, but for trying to understand better the entanglement that happens and is broken as you hit one of these large nuclei. And if you have a way of measuring the spin of pairs of particles, for instance, it would be a very huge tool that we could use experimentally. So I'm not familiar with any technique to do that, but if it were possible, it would certainly be really interesting and I think useful in many ways.
I mean, it was an informal discussion. I was looking for measuring for early time vorticity with photon polarization.
Right.
And yeah, I was talking to an experimentalist here, who's not here. Yeah, who kind of said that it's not too crazy type, you know.
Yeah, right.
Yeah.
I'll have to think.
Okay, fair enough. Thanks.
I would say it's definitely not. There's nothing naive about that. It's a good idea, and it's probably challenging, but maybe not impossible.
Sure.
Yeah. Well, so one thing I don't think this is quite what we're talking about, but if you have photons that are produced in the collision that convert on material, I have heard that if you have enough precision, so if you can measure the pair and reproduce the production location, and you know the magnetic field direction, I think there are some arguments that you could do a statistical analysis.
The idea was the idea was photons that convert into electron-positron pairs close to the calorimeter, and then you see, you know, and then it can act. I suppose it's a different momentum range from the dilepton pairs you're studying.
No, but this is okay. But that's kind of the picture I have in my head, and I think it should be possible. You know, these events are messy enough that as experimentalists, we're really good at ignoring things that we think are not important. And so, for instance, for a lot of analyses, you just ignore all conversion electrons because that's your material getting in the way. And for an analysis like this, that's where maybe you go back and look at them in detail. There could be something interesting there.
I see.
So,
I see. Thanks.
Alejandro?
Thank you, and thank you, Daniel. This was a very nice talk, and
thank you.
I think that motivating and also intriguing. What I wanted to do is to clarify the picture that I think I got from your presentation. Please correct me if I'm wrong.
Yeah.
So if you can go back to your slide where you show the different impact parameters of, you see, you have this spheres that collide. Well, no, these were the red spheres that collide. They were right of your slide.
This one.
No. There, that one, exactly.
Okay.
Sorry, there was a delay. is just to sort of put the question in context. So what I'm understanding is that when you speak about coherence, what you're saying is that the effect is produced by what we would call the spectators. I think that that's what you said here. In other words, that the photons that scatter are coherent, and that's because they come from the spectators, and that the small deviations of all of your observables that you showed come from deviations from this expectation of coherent scattering. And the question is, how is the overlap and the possible production of QGP in this overlap region can account? How can this account for these deviation of coherence production? Let me put it in another context. Imagine that you have a QGP forming these collisions. So although of course, since these are large impact parameter, the region that produces QGP may be smaller, but in any case, the point is that processes that originate, say, virtual photons that eventually decay in lepton pairs, they come from QGP processes which do not necessarily respond to a coherent field of the sort you have described, and therefore they may be a source of these discrepancies. Is that picture fit?
Okay, so
your picture?
Right. So so one of the handles we have on this is just the PT of the pair. So maybe actually, where did I put it? So here, this is a good example. So this curved line takes into account processes like what you're talking about. So when you have a hadronic interaction and you have, quark-quark fusion or gluon fusion or vector meson decay or whatever, virtual photon decay to dileptons, all of that is modeled in this curve. And the idea is that, the real experimental handle that we have is, as you can see, as you go to a PT of 0 for this pair, basically the idea is that all of these processes are very unlikely to produce a pair which has an E plus E minus, almost back to back. Because if they're just, if they decay, they'll probably have a smaller opening angle given by the mass. And if they're some kind of random contribution or some kind of like thermal pair, they're still not very likely to be back to back. So experimentally, that's the main way that we can distinguish these. However, just to be completely honest with you, we are trying to understand if, for instance, as we were just talking, this is the real world. We have conversion of photons. If you have, a block of something at a very specific location in your detector, sometimes it can produce structures that show up in PT and invariant mass space because it corresponds to the opening angle and the angle between the pair. So we're pretty confident in these results. Because what we can do is we can reject conversion pairs with some experimental techniques where you look at the opening angle with respect to the magnetic field direction. We can also just cut on our data because our detector is, a couple meters across, and we know where most of the material is. So we can cut on kind of the cleanest data, and we still see these features. So that's why we're really trying to understand if there could be a physics source for this. What I kind of was going a little fast at this point, but in my opinion, it's difficult because you have a couple of different things that could all give a very similar effect. So for instance, here, this was our old measurement. And the idea was that in this tail, you start to see something a little bit broader than the expectation. Well, once you have, higher quality data and more statistics like you see here, maybe that's not broadening due to Lorentz force bending. Maybe that's some other physics process which is contributing here and lifting this tail up. So anyways, long story short, we're pretty confident in this measurement. Otherwise, we wouldn't have released it. But until we can really explain this bump, I would say that we can't say for sure what is contributing. And we think there's quite a few interesting possibilities, and that's what we're trying to figure out.
Okay. Okay. Thank you very much.
Mm-hmm.
George, you still have your hand raised because you forgot or because you have another question?
I forgot, sorry.
Manuel?
Sorry, I'm coming. Okay, yeah. My question is exactly about this plot. Of course, I'm not very specialist, okay, but I am a nuclear physicist. So if you have a small PT, as you was showing, okay, this means that you need to be in some peripheral. No, I cannot understand what means small PT. Okay, here if you have two nucleus and they are really taking together. So explain me that, because what I know from nuclear physics is that all these electric field effects are really important in peripheral collisions. Okay, because after that nuclear force dominates, no? Mm-hmm. And so I'm a little bit confused how you can really, what means this small PT, okay, physically, okay, in the reaction, because
So you said what leads to this small PT?
Yeah, but what does it mean in the collision? How is this connected with the centrality of the collision?
Yeah, this is a very good question, because this was not so for many years the traditional EPA, the idea was that you have an uncertainty principle between the spatial position and the impact parameter. So in principle, you should not be able to localize the spatial the spatial separation and simultaneously measure a localized momentum distribution. So this is not a trivial matter. And let me see if in my backup I have some, I don't remember what I put here. So maybe I didn't put a slide specifically about this, but the idea here is that, so the idea here is that your transverse momentum is essentially, let me come back to this early slide. So I have this cartoon, right? And as your electromagnetic fields are Lorentz contracted, in the extreme limit, they're completely Lorentz contracted, completely in the transverse plane. And at that point, they become a real electromagnetic wave, real photons with no transverse momentum. But what we found is that because they're not quite contracted into the transverse plane, what it's like is that you have a spherical wave. So, so the photons, even though they're extremely low virtuality, it's like having a laser pointed at a small angle. Okay, so because the field isn't quite in the transverse plane, even though it's well approximated by a linearly polarized electromagnetic wave, it has a, kind of an angle to its transverse momentum. And as you go to larger and larger impact parameters, just by virtue of the fact that the same quasi-real photon has to kind of like travel way out here, it has to be at kind of a more shallow angle for the same lifetime. This is a little bit of a naive picture, but I think intuitively, hopefully it explains it to you. So what ends up happening is that if you probe photons very close to the nucleus, on average, they are higher transverse momentum. So that's what this picture here is meant to portray. So the real answer is that the photon's transverse momentum isn't conjugate to the ion-ion impact parameter, but it's conjugate to its own separation from the field that's emitting it. So for instance, you have this BPERP1. So the transverse momentum of that photon at that location, there's this conjugate uncertainty, principal relationship. But by fixing the ion-ion impact parameter, you don't actually fix the exact spatial location. You can still have production over all these different spatial locations. But what happens is you essentially end up with a weighted average. So my point with this slide is that you end up with predominantly pairs where you have one very long-range photon, which has very small transverse momentum by this geometric picture, and one very short-range photon that has higher transverse momentum. And that's why if you go into these UPC events where you're at large impact parameters, you have a sharp peak that's kind of focused around this relative distance. And then as you move to these smaller impact parameters, like I show here, you end up having a much more, a smaller spatial region that you're weighting, and you are much closer to both sources. And so now you're actually, you're basically, you have the contribution of two higher momentum photons. And that's why when we go from UPC, which is large impact parameters, to these glancing collisions at small impact parameters, you actually do have a trend towards higher pair transverse momenta because of the fact that you're constraining the photons to interact much closer to the two nuclei.
Okay, so if I understood, so small pt in this sense means let's put spatial long photon in that sense.
Yes.
So
Yeah.
why you expect that in that case the electromagnetic effect is going to show up in some sense more than the other case? Is that more or less? Yeah.
So I'm not sure I heard all of it, but your point is, so how do you know this is electromagnetic?
Yes, because could be a hadron effect. So let's understand why it's electromagnetic really.
Yeah.
So I understood now. So you say that.
Right. Well, okay. So there's two answers here. So it's, again, you can back of the envelope, you can calculate the order of magnitude for the transverse momentum you expect here. And it's given order of magnitude by 1/r, whatever r is for the source. And so 1 about 7 Fermi, 6 or 7 Fermi, is about 20 MeV. So that gives you the order of magnitude, and that's why. So if you're going to have these photon-photon interactions, 20 to 30 MeV is where you expect it. Now, the other side of your question is, how do you know it's not hadronic interactions? And again, we have, we do have Monte Carlo and event generators that provide us, like Hygiene, URQMD, lots of different models that provide for us a pretty good picture of a standard hadronic collision. And if you take all of the electron-positron pairs that are produced, and you look at their momentum, you find that hadronic sources do an extremely good job of describing it at high PT. And then as you go to this lower PT, you get this very smooth transition.
Nice.
So, I mean, my point is that there is still something here we don't understand. So I can't promise you that we're, 100% free of some hadronic effects. But, in this, I can zoom in here. This QED prediction, which is this coherent photon-photon interaction, describes this measurement extremely precisely. So I don't think we have any doubt that this part is coherent electromagnetic process. I'm personally not convinced what this bump is. So I think that needs more work, and we may find it's from hadronic process we didn't know about, or it's from some other, like I point out here, some semi-coherent electromagnetic process.
Okay, thank you very much. Thank you.
Yeah, thank you for the question.
More questions?
I guess I have a quick question. Sorry, can you go to the charge radius?
Yeah.
Rise with energy. You had this you know, the plot where they charge radius, skin depth.
Yeah, is it there now?
So yeah, I see it. So the hint of the rise with energy are these color codes, right?
Yeah.
Yeah. Did you guys try to compare? Because there is a rise in cross section and there in scattering cross section of nucleons, and there is interpretations of this in terms of pomerons and stuff like this. I'm just wondering if the charge radius and the cross section radius are sort of the growth is comparable, or so if you guys check, if you can check this. Yeah.
Right. No, so it's really out of scope for the seminar, but actually I just posted a paper on archive yesterday.
Giorgio, maybe you can mute your micro. Yeah, thank you.
Yeah, thanks. Some feedback. So we just posted a paper, basically what I've been working on since this, on archive on Tuesday. And long story short, I mean, I don't know how much time you guys have, but long story short, we use the fact that the photons are linearly polarized to study these photonuclear events in a new way. And by doing that, we can measure the mass distribution at the precision of about 1/10 of a Fermi. So as far as I know, there's been no technique to do this in high energy collisions. So now with these photo processes, the two-photon process and the photonuclear process, we have a way of looking at the charge distribution and the mass distribution at high energy. And what we see, in fact, is that there is so the nucleus looks a little bigger than what you expect from low energy scattering. You can either interpret that as a neutron skin, or you could interpret it as swelling as you go to these higher energies. So we've definitely thought about what you're mentioning. You know, like many things, it's very hard to pinpoint a specific mechanism or a specific interpretation. But I think it's getting very interesting, and I'm really hoping that with, you know, I pointed out that STAR has all this data planned. Well, maybe I don't have a good table of it, but yeah, anyways, we intend to collect 20 billion gold events in the next 2 years. This will be our largest data set, and we're really hoping that we can revisit these measurements with really high precision and address the topic that you just brought up. So hopefully I'll have something exciting to tell you in a few years.
Thanks.
Okay, so we had already a long question
thank
session.
you.
So thank you very much again, Daniel.
Yeah.
Yeah, for the very nice talk and replying the questions. So we hope to see you here in October.
Oh yeah, I would love to. So we speak Spanish some. My wife is from Cuba actually, and she's been studying Portuguese. So maybe if we come speak a little bit, we'll see.
Yeah. Let me know when you know.
Yeah, it should be soon.
You listen a lot of Portuñol. It's yeah. Portuguese and Spanish together we talk.
Exactly. Like Spanglish, but Portuguese and Spanish.
Okay, so I stop recording.